Assalamualaikum and hello listeners. Thank you for tuning in to our physics outreach video. Today, we will be learning about buoyant force and Archimede'S principle. Let's take a look at what today's video will show us. First of all, let's learn how Archimede'S principle are first discovered. In the earlier day, Archimedes decided to take a bath in a tub while trying to find ideas to resolve the dilemma of the king of Syracuse. Then, he realized that when he stepped inside the bathtub, water splashed out. The more he stepped in, the more water got splashed out of the bathtub. He then concluded that the amount of water displaced must have a correlation with his body volume, and this then leads to the discovery of Archimede'S principle. Now that we know the history of Archimede'S principle, let's move on to the definition of buoyant force. So, what is buoyant force? Buoyant force is the force acting upwards on an object immersed in a liquid when there is pressure difference between the lower surface and the upper surface of the object. Let's look at the diagram shown. In the diagram, the pressure acting on the top surface is labeled as P1, while the pressure acting on the bottom surface is labeled as P2. The force acting on the top surface is labeled as F1 and the bottom surface F2. When the pressure at P1 increases, the force at F1 also increases. The same occurs at P2 and F2. When we deduct the force at F1 from F2, we will get an upward resultant force, which is the buoyant force. How does buoyant force relate with Archimede'S principle? The principle of Archimedes stated that an object which is partially or fully immersed in a fluid will experience a buoyant force equal to the weight of the fluid displaced. To make it simpler, let's imagine that we are holding a glass on our right palm, with the left palm covering the top of the glass. Now, when we push our left palm down and our right palm up on equal pressure, the glass does not move. However, when our right palm exerts more pressure than our left palm, the glass moves upwards. When the opposite occurs, the glass moves downwards. To make sure we understand the general theory of Archimede'S principle, an experiment can be conducted. This experiment is very simple, where first you weigh the weight of the object, then you put the object in the beaker slowly until it reaches the bottom. The amount of water splashed out will be measured on the electronic balance. To make the experiment clearer, let's watch the demonstration of the experiment conducted by one of our members.
So, let's proceed for the experiment. Firstly, we need to have measuring cup as a replacement for eureka can, the object, the weighing scale, and also the glass. Firstly, we need to take the measuring cup near the glass and make it slanted. Take the object and put it down to have the water displaced until it sinks at the bottom of the cup. So, we have the reading for the mass of the water displaced. So, we need to change the 40 gram into weight, which is by using the formula weight equal to mass times gravitational acceleration, and then we got the weight of the water being displaced, which is the buoyant force. Thank you.
From the experiment and demonstration, we can conclude that first of all, the weight of the object in air is the real or the actual weight of the object. When the object is submerged in a liquid, the weight of the object in liquid is the apparent weight of the object. The object then displaces the liquid. The volume of the liquid displaced is equal to the volume of the submerged part of the object. This means that the deeper the object is into the liquid, the more liquid will be displaced. When we deduct the weight of the object in liquid from the actual weight of the object, we can see the object experience apparent loss in weight. This is the weight of liquid displaced, which is also equal to the buoyant force acting on the object. Hence, we know that buoyant force Fb is equal to PVG, where P is the density of the fluid, V is the volume of fluid, G is the gravitational acceleration. Next, let's look at the states of buoyancy. In total, there are 3 states of buoyancy depending on the weight of the object. If the weight of the object is equal to the buoyant force acting on it, the resultant force is 0, meaning that the object will be stationary. If the weight of the object increases and become larger than the buoyant force, the force will be unbalanced, which means that the object will move downwards with acceleration. On the contrary, when the weight of the object is smaller than the buoyant force, the force is also unbalanced. However, in this case, the resulting force produced is upward, which means that the object will move upward with acceleration instead of downwards. Well, we have understand the theory on how buoyant force and Archimede's principle works. But what use does it have in our daily life? Let's take a look at the first application of Archimede's principle. A ship, though very heavy, floats on the surface of the sea. Ships, large ships in particular, are generally made from steels, meaning that it will be very heavy. On top of that, steels are denser than water, which means that naturally the ship would sink. However, it stays afloat. How is this possible? If we look at the anatomy of a ship, it is not made from solid pieces of steel. Instead, the inside of a ship is actually hollow and filled with air. As a result, the weight of the ship is equal to the buoyant force acting on the ship. Hence, the ship floats. In order to make sure the ship is loaded within limit, plimsoll line is marked on the body of the ship. Next, submarine, which can float as well as dive in water, also apply Archimede's principle in its mechanism. Submarine have a watertight outer hull with tanks known as ballast tank inside the hull. These tanks are the key to control the position as well as the depth of the submarine. When the ballast tank is empty, the weight of the submarine is equal to the buoyant force or the upthrust acting on the submarine. Hence, the submarine floats. In the contrary, when the ballast tank is full, the upthrust or buoyant force is less than the weight, causing the submarine to accelerate downwards. Both the two previous applications took place in water. Now, we are going to see Archimede's principle being applied on air. The next application is hot air balloon. As we know, the density of hot air is less than the density of cold air. Inside a hot air balloon, there is a gas burner which can be turned on and off according to the needs. This is how the height of the hot air balloon is controlled. When the gas burner is turned on, the air heats up. The buoyant force acting on the hot air balloon is more than the weight of the hot air, the weight of the airship fabric, the weight of the gondola, and also the weight of the passengers combined together. Hence, the hot air balloon rises upwards. To make the hot air balloon move downwards, the gas burner is turned off and the air is let to cool. Here, the buoyant force is less than all of the weight mentioned before combined, allowing the hot air balloon to move downwards. The hot air balloon will remain stationary when the buoyant force is equal to all of the weight combined. The next application is a weather balloon. A weather balloon will float up when it is released. It is usually filled with hydrogen gas, which is less dense than air. When the buoyant force acting on the weather balloon is bigger than the weight of hydrogen, balloon and radiosonde combined, the balloon will float. On the other hand, the balloon will remain stationary when the buoyant force is equal to all of the weight combined. Radiosonde will send back the information on atmosphere pressure, temperature, humidity, and wind speed to weather station. The weather balloon is normally released early in the morning because of the low temperature that causes the density of air to increase. Hence, the balloon can flow easier. With that, we have reached the end of our video. We hope that you will get to learn more about Archimede's principle through this video. Thank you for watching.